I'm going to take my oscillator and I'm going to put it into my filter. So if I have an LFO, and remember my low-pass filter, for example, if I have my low-pass filter set up, I have one variable in my filter, which is the cutoff frequency amount. And we talked about before, if I move that cutoff frequency to a certain point, then it's going to allow certain things to pass or not. But now, imagining my LFO as a control device, which is going to be controlling the filter frequency. So I can now take control of that filter, as opposed to moving the filter cutoff frequency manually. I can have my LFO control that. So if I assign this to the filter frequency, and let's set it up on a sine or a triangle waveform again. So now what's going to happen is this cutoff frequency, rather than moving it manually, and I'm going to move back to a sawtooth waveform as my carrier here. So if I have a carrier that is a sawtooth waveform, it has, remember, all the overtone partials in it. And then if I have this set up to control the filter of that, a low-pass filter, then when I play this, the cutoff frequency will be controlled by this LFO here. Let me slow it down. So what you're hearing is this filter cutoff frequency moving up and down, but it's being controlled by the LFO. So we're getting a timbral change because I'm now filtering out or attenuating some of the partials according to this is a low-pass filter, but I don't have to do it manually. I can have this LFO change that cutoff frequency for me. And I can change the speed of that. Or the amount of how far up and down the filter goes. So this is not a frequency change, it's not an amplitude change, it's a timbral modulation. I'm actually allowing for the overtones to come into the sound and then to go out of the sound by moving the frequency through the LFO. Now what would happen if I change my filter to a high-pass filter and do the same thing? Remember, the high-pass filter attenuates all the frequencies below the cutoff frequency. So what I'm hearing now is the filter is still moving, the cutoff frequency is still moving, but what's happening is it's only allowing the upper partials to pass. And then go back to the low-pass filter. Same thing is going on, but now it's the frequencies, the fundamental and the lower frequencies that are coming through, so it sounds louder to us. If I go into a band-pass filter, you'll hear just a band that we're allowing to pass through. And then the notch filter, the band reject filter, I'm just cutting out a certain overtone series as it moves up and down. So with a simple LFO, assigning it into your low-pass filter, we get another series of timbral modifications that can happen over the time. So once again, if I have my low-frequency oscillator, which is, in this case it can be a sine wave or whatever, I can plug it into the oscillator, the carrier oscillator. I can plug it into one of the modifiers, the VCF, or I can plug it into the VCA, doing some kind of modulation or change to the sound, either frequency, which is what the oscillator would do, or timbre, I would change with the filter, or amplification, amplitude, I could change here. And that's just with the LFO and one of those devices. So this is what I refer to as sort of simple modulation. Simple modulation meaning I'm not creating any sidebands. I'm just keeping it, and simple means that the control oscillator has to be an LFO. It has to be below the hearing range in order for no other acoustical information to be created. So now let's take a look at what happens when we take these control oscillators and move into the audio range. So I'm going to go back over here and start with my VCA. I'm going to put my sine wave in there, but rather than an LFO, I'm going to move that into the audio range. So let's say I'm set up with, and I'm going to go back to make this simple, less complicated, I'll make it a sine wave. So I have a sine wave carrier. I've got it at 500 hertz. And the filter, I've got the cutoff frequency at the top, so it's not really doing anything. And then I have this VCA, and it's being controlled by a control sine wave oscillator, and it's set up at around 100 hertz. So this is not an LFO. We can hear that's in the hearing range, but I'm not hearing, it's not plugged into the mixer. I'm not actually hearing this sine wave, because what it's doing is just going to be modulating the VCA, and it's going to be changing its amplitude up and down like we heard with the LFO, but we can't hear the individual changes. What we hear is the cognitive impact of sidebands being created. So whenever you have, and this might be referred to as complex amplitude modulation. So complex AM is what we're talking about now. What will happen in this arrangement is that there's a phenomenon where we take the carrier frequency, so the 500 hertz comes through, because we can hear the carrier, but when I have this complex AM amplitude modulation arrangement in the VCA, what happens is with a sine wave modulating a sine wave, the sine wave will combine itself with both addition and subtraction. We add the 100 hertz signal to the 500 hertz, and then we subtract it. So what happens is we get, coming through this, we get a 600 and a 400 hertz signal coming through. If I lower the frequency of this, say down to 50, then I would get 550 and 450 sidebands. So there, with a sine wave modulating the sine wave, there are going to be two sidebands, two extra frequencies created. So let's see if we can hear that phenomenon. Now remember, here we have oscillator 1, and the LFOs cannot really go into the audio range, even though we can barely, we heard before, we can barely get into that. But what I can do here is to take the oscillator 2, and I'm going to set these on sine waves again so that we don't get any confusion as to what's going on. It'll be a sine wave modulating a sine wave. I'm going to tune this one, and I can't see on this particular device, I cannot see the exact hertz. I can see just a kind of a general setting. I'm going to take this one as an octave below the oscillator 1. So what I will do is I will have oscillator 2 that will be assigned into oscillator 1. So now with an LFO, we can take this amount up, and remember we're doing amplitude modulation. So first of all, we hear the LFO doing a amplitude change. As we increase the rate higher, we move into the audio range. And you can hear the two sidebands. As I move the frequency up or down, you can hear a higher pitch and a lower pitch start to move around. That's why I'm changing the frequency of my control oscillator. So now we're getting sidebands, and these sidebands are moving around as I move the frequency here around. As this frequency goes up or down, then it's going to determine, it's going to be adding or subtracting what I'm doing to here. So the carrier is still going through, but we're now hearing these other pitches. And think about this for a second. If I set up my control oscillator, let's say my VCO is at 500. What's going to happen if I assign my sine wave oscillator also at 500? So that what's going to go through is, here again, you add and subtract this frequency to the carrier. So we have the carrier that goes through, that's the 500. And then we add this, we get 1,000 hertz. And then we subtract this, which means we're going to get 0. Those are going to cancel each other out. So in this case, if you assign the same frequency here, we will basically get one sideband that's created twice this, which, what is remember again, what is a 2-to-1 ratio? A 2-to-1 ratio is going to give us the octave in our overtone series. So if I want to create an octave harmonizer, which many devices do, you do that by assigning a sort of complex amplitude modulation, assigning the same frequency to your carrier and your control oscillator. It produces the octave above it, but then cancels out the sideband below it, so then you just get that octave. So that way we can, and anytime I move my VCO, my oscillator, if I change pitches, so let me see if I can do that here. I may not be able to find exactly the octave. Let's see if I can. I can't quite get the octave because this LFO would allow me to go up there, but you can hear the potential. So if I were to move around my pitch, my primary fundamental of the oscillator 1, so the sidebands go with it. So then you get this parallel effect. If I could get this tuned to an octave, then you would hear the harmonizer just doing an octave above it. Anytime I change the fundamental frequency, it's also changing the same one on the secondary oscillator. So that's a very interesting kind of relationship that you can do with just here again modulating the amplifier in a complex AM, producing two different kind of sidebands, or you can also just have one with the other attenuated. There's another type of variance, which is another type of amplitude modulation that you'll find a lot of in synthesizers, and that's referred to as a ring modulator. The ring modulator, many times in our block diagram, you will see not a VCA, but you'll see something sort of like this, and then you'd have your control oscillator going into it. The ring modulator, often RM, it does a similar effect to amplitude modulation. One of the differences is it will attenuate the carrier. So in a ring modulation, you will have an effect of ring modulation because it's only the sidebands that are being put with that, and the carrier does not go through, is attenuated. So whatever you have on the two sidebands that are created will come through. And then there's an amplitude change. The amplitude of the carriers will be greater in a ring modulator than an amplitude modulation. So you do get some slight differences. But ring modulation was one of the very first synthesizer techniques that was found that Stockhausen and a lot of people in Cologne in the early 50s, when they started experimenting with analog synthesis, they used ring modulators, and then they would also use amplitude modulators for creating these other sonic effects on that. So ring modulator is something you'll find often on synthesizers, and sometimes it'll just say amplitude modulation or ring modulation, but they're slightly different in the way they result in the output coming through. All right, so that's amplitude modulation.
The preceding program is copyrighted by Emory University.